my real pleasure to introduce Professor Victor Ostrik. So he's known of his work on various aspects of tensor categories, and he was a recipient of Chevalier Prize of the American Mathematical Society this year. He's now a recipient of Frontier Prize here. So Victor, welcome. And just one more comment. This is a beautiful subject which can be classified as asymptotic representation theory.
So, right? Yeah, it's our first steps in this direction. Thank you very much for your kind introduction, and thanks very much to the organizers for inviting me here. And thanks so much for all the volunteers who made this event possible. So I will talk about several papers written jointly with K.Coulembier, P.Etingof, and D.Tubbenhauer in various combinations. So let me start. So this talk is about linear representations of groups. So let me start from the very beginning. So you start with some field and take some finite dimensional vector space over this field. Then you can consider group of invertible linear operators from this vector space to itself. Of course, if you choose basis of vector space, this group identifies with group of invertible matrices. And now take absolutely any group, anything that you like. So integer, symmetric group, braid group, free group, whatever. And here's main definition. So linear representation of a group is just a homomorphism from group gamma to this group of matrices. And well, in this situation, we're going to say that this underlying vector space V is modulo of a group. And here is kind of example to keep in mind. If your group is a symmetric group, you can consider representation where elements of symmetric group act by permuting elements of some particular basis. So in other words, they act by monomial matrices. So this is kind of one example. And well, important thing here that representations are considered to be the same. So representations are equivalent if they differ only by change of basis in vector spaces. So basically all these matrices that you see are conjugated by one fixed matrix. Okay. Now let us discuss some basic operations on representation. So one operation is the operation of direct sum. So if you have two representations, you can build new one just by writing block diagonal matrix. Well, this is gives you new representation, and it's kind of considered to be very trivial operation. So there is not much to say here, but you can make it interesting if you think about this backwards. So I will give you some representation, and I will ask you, well, whether it decomposes into direct sum or not. Try to decompose it, and this makes things much more interesting. Okay, so here's again easy example. So if you take symmetric group S3 and representations of which considered on previous slide, and if you choose bases differently, not take this kind of first obvious basis, but choose some little bit strange basis, it's actually going to be basis only if characteristic of your field is not 3. Then you see that any matrix representing elements of any element of symmetric group is going to be block diagonal like this one. And this basically means that my representation decomposes into direct sum of something one-dimensional, so this kind of left upper corner, and something two-dimensional. One basic result is K.Coulembier theorem, and it says that any representation always decomposes. I mean, you can decompose it until you can. When you can't decompose it anymore, every summand is indecomposable representations that you cannot indecompose anymore. And this is essentially unique in the sense that summands are uniquely determined up to permutation. Here is kind of standard fact. So if you take symmetric group as 3, then and if characteristic of your field is not 2 or 3, then there are just 3 indecomposable representations. So 2 of them were already seen. This is U and W, and there is one more U minus, which is one-dimensional, and which send every permutation to its side. And by the way, for representation U, every permutation sent to just to one-by-one matrix with one inside of it. So that's very simple one, usually called trivial representation. Well, this is a little bit exceptional situation. So if you will take your really favorite group and will try to classify indecomposable representations, most of the time it's going to be what is called a wild problem of linear algebra, which basically means that there is no hope to come up with classification of indecomposable representation. It's kind of too difficult of a problem. And well, when we teach this in graduate classes, we start with actually exceptional situations. So if group happens to be finite and characteristic of your field is 0, well, in this case, complete classification is available, and that's easy thing. Okay. Another operation. So another operation on representations is operation of tensor product. So if you have 2 representations, you can take the tensor product. So in terms of matrices, you are supposed to take what is called Kronecker product of matrices. And it's much easier to think about this abstractly. So underlying vector space of my representation is just tensor vector space of representations, and action is given by kind of quite obvious formula on quite obvious, but unfortunately written with mistakes a formula here. Okay. Well, this operation, it's easy to see that it's associative, commutative, it's unital, it has units. So there is some particular representation such that when you tensor with this representation, you'll get the same representation back. It's trivial representation. It also distributes over direct sums. And this means that if I want to compute all possible tensor products, it's enough to compute tensor products of indecomposable representations. And in my example with symmetric group S3, here is multiplication table. I have 3 representations, and this is how they multiply. So really interesting entry here is this one. So all the others are kind of relatively easy to get. But even this one is easy exercise. Okay, so now finally, let me talk about subject of my talk. So, well, let us take any group, any field, any finite dimensional representation of this group, and let us form tensor power. So I'm going to do this operation of tensor product many times with one particular representation. And well, let us do this converse problem about decomposition. Let us decompose this representation into direct sum of indecomposable ones. And it's actually important and interesting problem of representation theory to understand anything about this decomposition. Just say anything and this would be useful. But let me concentrate on probably simplest possible aspect of this. So, well, there is some number of summands here. So how many summands are in this decomposition? That's the question which I want to investigate. So, well, here's my question. So say anything non-obvious about this sequence. It's a sequence of integers, non-negative integers. Actually, it's kind of almost obvious that this increasing sequence. What else? Well, just to be concrete, maybe let me try to study how fast the sequence grows. Reasonable question. And well, I have one representation W, and if you compute this sequence for this representation, you will get numbers like this. And well, maybe you can guess the pattern, or you can just try to compute what this pattern is going to be. So if n's tensor power is a combination of u minus, and w with coefficients an, bn, cn, then my multiplication table previous slide gives me some recursive relations for these numbers. Well, and if you solve these recursive relations, you can find maybe one of them. And from this, you can find my sequence Bn of W, and probably you already guessed what answer is going to be. So that's, well, actually, I really want you to remember this formula. It will appear again. Okay, If I'm interested in growth of this sequence, well, clearly this term with 2 power n plus 1 is much bigger than another term. So kind of it really controls what is going on. Okay, any questions? Okay, so maybe this computation justifies the following theorem. So again, in the same setup as before, any group, any representation, any field, I expect my sequence to grow exponentially. Well, if you want to measure how fast it grows exponentially, you can compute this limit of nth root of my sequence. And answer is that in all cases, you are going to get exactly dimension of your representation. So that's kind of theorem. So maybe nice thing that this is very, very general statement. Let me illustrate this theorem. So actually you will see, hopefully, that this theorem in many cases is actually quite easy theorem. And in many cases, this theorem is definitely not end of the story, but just beginning of the story. So that's kind of next thing which I want to explain. So here is example from graduate class in algebra. So if my group happens to be finite and my base field is complex numbers or really any field of characteristic 0, then we have finitely many possible indecomposable representations. You can take M to be maximal possible dimension of this. And then it's kind of obvious that my sequence Bn is squeezed between dimension of V power n and dimension of V power n divided by this particular number m. Just because any summand, it contributes at least one dimension in the total direct sum, or at most m dimensions in the total direct sum. That's it. And if you take nth root of this inequality, you'll get this yield. That's kind of very easy. Same logic applicable if for my group I have just finitely many indecomposable modules. You take this M for maximal possible dimension of this indecomposable module and you are fine. Or maybe even more generally, if you have some bound for dimensions of indecomposable modules. So unfortunately, this is very, very rarely the case. So kind of it's not really generic thing. So let me discuss next case. So now my group gamma is still finite, but my base field is of positive characteristic. So if you take kind of typical situation here, then gamma will have infinitely many indecomposable representations of arbitrarily large dimension, and there is no hope to classify them or anything. However, gamma has only finitely many projective indecomposable modules. So these are modules which appear as direct summands of a regular representation. Well, if you want to prove theorem similar to, I mean, my main theorem, the following result is really helpful. So if you have faithful representation and start taking its tensor powers, sooner or later you are going to see projective summand. That's kind of a theorem. This theorem has the following corollary. So it turns out that if you will see one projective summand, after a while, this projective summands take over. So kind of almost all summands and tensor powers are going to be projective. And in a sense that kind of if you will combine all non-projective summands, their dimension is bounded by something like geometric progression with denominator which is strictly smaller than dimension of V. And reason for this corollary is that projective modules, they have a kind of ideal property. If you have projective module, tensor it with any other module, you'll get again projective module. So that's kind of really the only how you deduce this corollary. And this corollary is good enough now to deduce my theorem. So kind of you play the same game, but you just basically take into account that all these non-projective summands, they contribute just a little bit. And projective summands, I have some bound for their maximal dimension, and you will have some inequalities, and this is good enough to deduce this theorem. So that's modular case. That makes sense? Okay. So little bit more. So if I want to understand my sequence a little bit better, so we know that it grows approximately as dimension of V power n. You can ask for more precise results. So kind of maybe first thing to ask is what is going to be limit like this. So you take Bn of V divided by dimension of V power n. Well, what it might be. Well, You will see in a second that in general it fails to exist. However, it does exist for V, which is my W from the very beginning of this talk. And anybody remember, can tell what this limit is going to be? I told you to remember this formula. Well, yeah. Well, it's close. So it's going to be 2 over 3. So 2 over 3. Say it again. Not total number, no, but close. Yeah. Anyway, homework. Try to deduce formula in general. So here is example where this limit fails to exist. So if you take dihedral group of order 8 and for V take unique irreducible two-dimensional representation, then it's really easy to see that this ratio Bn of V divided by dimension of V power n, it just oscillates between 1 and 1/2 depending on parity of n. So, and well, in particular, you don't have any limit here. It's too bad, but actually it's not too bad. So you have two subsequences. For one, limit is clearly 1, and for another, limit is clearly 1/2. So that's kind of what is going on here. It turns out that for general finite group and absolutely general field F, you have something very similar. So you look at this sequence, it has finitely many limiting points. All limiting points are positive. Actually, they don't really depend much on representation. They depend only on things like kernel of this representation and maybe projective kernel of this representation. So it's elements of a group which act by scalar matrices in this representation. Actually, very similar to my example with dihedral group, you can split whole sequence into a bunch of arithmetic progressions, and for each arithmetic progression, you'll have some particular limit. So kind of like in this example here, so we have even numbers and odd numbers, and for both of these arithmetic progressions, we have a limit. So that's general situation. Okay, and now let us move to infinite groups. So my favorite infinite group is group SL2. So SL2, well, as an algebraic group maybe. So let me start with discussion of a characteristic zero case. So, and let us take most obvious representation, two-dimensional representation of this group. My sequence is really easy to compute in this case. That's again exercise for graduate students. So character of tensor power is just q plus q power minus 1 power n. And from this, you deduce that my sequence is exactly given by middle binomial coefficient. So binomial coefficient, which is exactly in the middle. And if you use Stirling formula, you will deduce asymptotics. And something new is going on here. So it's dimension of V power n, but in the denominator, you see n power 1/2. So it's kind of, it's different behavior from before. So there is no limiting points as before. I mean, if you divide the sequence by dimension of V power n, ratio goes to 0, and it goes to 0 in kind of in very specific way. So that's maybe more interesting. You can try to repeat this exercise with three-dimensional representation. And well, it's very similar, but in this case, you see that there is no much hope for nice formulas for the sequences. So in this case, my sequence Bn is going to be given by free term of polynomial q squared plus 1 plus q power minus 2 power n, and there is no nice formula for this. I mean, you can write some formulas, but they're not really nice. However, if you know some probability theory, and if you employ central limit theorem, you will get easily asymptotic for this free term, and asymptotic is 3 power n, again divided by n power 1/2, and there is some constant, which is actually computable. Does that make sense? Okay, so there is a generalization of this for all possible reductive groups. So actually this generalization was, well, it seems like at first was discovered by Philippe Bian, but then rediscovered by many people. I think it includes Scholar here, and it definitely includes me and my co-authors. And so on. So answer is very similar. So if you want to study the sequence Bn of V, well, you are going to have dimension of v power n divided by n to some power, and there is some constant. I want to concentrate on this power here. So power here is actually number of positive roots of my reductive group divided by 2. So what is important here is that this number is half integer. I mean, we've seen 1/2 in case of SL2, or in case of SL3, you will see 3/2, and so on, since like this. Okay. We will go to SL2 for modular situation in a second, but let me first say a little bit about, well, a little bit side topic. So if you know something about your sequence Bn, you can say something about group gamma. So here is example. So let us be in the case of characteristic 0, and let us take algebraic group such that its connected component is just a torus. And in this case, well, all representations are completely reducible, and it's really easy to come up with upper bound for any reducible representation, and maybe it's again exercise for graduate students here, and hint is used for Daniel's reciprocity. And this gives some inequality like this, well, so what is going on here? Bn of v is greater than dimension of v power n multiplied by some constants. That's kind of all I want to say. And here's a theorem. So conversely, assume that you are in characteristic 0, and assume that what you know about the sequence Bn of v is similar information. So it's greater or equal than dimension of v power n multiplied by some fixed constant. So you're in a situation like this. And basically, the theorem says that this example above is the only option for under this condition. So that's, I think, kind of something interesting. So growth really allows you to recover some results about your group. And you can do even better. So you don't really need this constant. You can have constant divided by n power alpha, but it's really important that this alpha is less than 1/2. So, well, what I don't know is how to remove assumption about characteristic 0 here. So it would be really, I think it would be interesting. I don't even know what might be conjectural statement in positive characteristic case. Okay, let's move back to SL2 in modular case and for positive characteristic case, and let's try to see what is going on here. So absolutely the same situation as before, but my field is now of positive characteristic. In this case, it's known that this tensor power we study is direct sum of so-called tilting SL2 modules. And main point here is that we know, I mean, there's some specific SL2 modules, and we know a little bit more about them than about general SL2 modules. Tilting modules were invented, I mean, introduced in this setup by Steve Donkin, and thanks to his work and work of Henning Andersen, you can work out some combinatorial description for my sequence, and you can do some numerical experiments with this. You can make computer to compute this, and you are going to get something which looks a little bit strange. So kind of this sequence is squeezed between 2 power n divided by n to some power with some constants, but these powers look strange. So kind of these numbers which appear, so alpha 2 is number which appears in characteristic 2, alpha 3 is number which appears in characteristic 3, and so on. And it turns out that you can compute these numbers. So theorem which, well, theorem basically says that it's not just numerical, but actual fact. So you can prove something like this. It was proved by Michael Larson and also independently by K.Coulembier, P.Etingof, Tubbenhauer, and myself. And well, I have formulas for these numbers. So these numbers are given something like this. You can do little interpolation and find this number for any prime characteristic P. So what is interesting here is that these numbers are transcendental numbers. So it's very much different from characteristic 0 case where these numbers were half integers. So that's kind of strange, well, I think surprising feature here. So you can think about these numbers as maybe counterparts of scaling dimensions in physics, or maybe Hausdorff dimension in topology. And for us, kind of appearance of these transcendental numbers, it kind of indicates that something fractal is going on in modular representation theory. So that's kind of one possible interpretation of this. maybe another interesting thing that, well, my sequence Bn of v is squeezed between kind of two constants multiplied by this 2 power n divided by n to some power. However, we do not expect that Bn of v divided by 2 power n divided by n to this power alpha p approach any particular limit. It's kind of, it still oscillates with n, so kind of behavior is more complicated than previous. So that's citation here. Well, this is very only beginning. So you really want to know what happens for other representations of SL2. Well, hopefully, so for SL2 in characteristic 0, this power n power 1/2 appears for all faithful representations. Well, maybe the same is true here, or maybe not, I don't know. And well, if you're really ambitious, you can try group SL3, and that's going to be, well, at least with current knowledge, it seems to be very, very difficult. And actually, it's not even clear. I mean, I have no idea what counterparts of these numbers are going to be for us. Okay, so let me just say a little bit about proof of this theorem. So just to get some idea. So I made this kind of big point how general this theorem is. And this is kind of misleading. So in fact, if you want to prove this theorem, you have to prove it only in one special case. You can take for group gamma group GLV, algebraic group GLV, and for modulo with this group gamma V itself. So GLV by definition acts on V. And this is just because if you have some bound for this group GLV, so kind of number of summands in this V tensor power n decomposes into some number of summands for GLV, well, then you restrict this decomposition to gamma, and you get maybe even more summands for group gamma, and this gives you some lower bound for this sequence. So that's it. And actually, when you realize this, you already proved this theorem in case of characteristic 0, because for characteristic 0, we have this nice bound for reductive groups, and GLV is a reductive group. And in positive characteristic, you just use theory of tilting modules. So tensor powers of V are tilting modules for GLV, and well, you use what you can. Maybe a little bit remark that this theorem is even more general than I stated. So you can replace gamma by Lie algebra. If you want, you can do instead of group semi-group. If you want, you can do supergroup instead of group. Super Lie algebra, some quantum groups. You can even forget about group gamma completely and just take V to be some object of Tanakian category, and you have something like this. However, it's not too general, so you can come up with counterexamples for some situations. So, for example, for comodules over some Hopf algebras and so on. So it's quite general thing, but not too general. Okay, so now I want to switch gears, and I want to discuss some related but different things. Are there any questions at this moment? Okay, so we can try to count this indecomposable representations in a tensor power of V differently in some other ways. So here is kind of one possible approach, so which was suggested by Benson and Simons. So let us go back to this case when group is finite and characteristic of our field is positive. So well, if you remember, when we discussed this case, we realized that if you take this tensor power, after a while, almost all summands that you see, they're projective modules. So kind of almost everything is projective modules, and there are so many of them that you don't care about the remaining modules. Well, so what Benson and Simons suggested, just ignore these projective summands and count only non-projective summands in this V tensor power n. And actually not count them. So they really want to take the total dimensions. So just take sum of dimensions of this guys. It's going to be important. And well, then you define invariant just in the same. So now again, I expect the sequence to grow exponentially. And in order to measure this rate of this exponential growth, I compute this limit. So And Benson and Simmons proved a bunch of results about this limit. So it's kind of an interesting invariant of representation now. There is no answer for this right away. It's just kind of something interesting, but not obvious. For example, this limit is not always an integer. So before, remember, it was just dimension of v. This limit is always between 0 and dimension of v, and well, it's 0 only for projective modules. If it is greater than 0, it's extremely easy to prove that it's greater or equal than 1. But now next result is very interesting. So if this number happens to be not 1, but slightly bigger than 1, so next possible value is at least square root of 2. So there is nothing between 1 and square root of 2. It's kind of should remind situation in subfactor theory where indices of subfactors are quantized and things like this. That's maybe more interesting thing. Conjecturally, this number is always an algebraic integer, but it seems like this is very difficult conjecture at this moment. You can show by examples that in general, this number is not additive and is not multiplicative. So if you want to compute it for direct sum, it's not sum of values for summands. If you want to compute it for tensor product, in general, it's not product of values for vectors. And maybe most interesting result is that if you can compute this number just in the case when gamma is elementary abelian group, you are good. You can compute it for any other group. But well, elementary abelian group is very, very difficult in this setup. So representations of elementary abelian groups are very, very difficult. Okay, so just to remind, so in this setup, this sequence Cn, it counts total dimension, and before we counted kind of total number of summands, you can consider similar sequence where you really count non-projective summands and define limits similarly to above. And I think in this case, it's not even known that this limit exists. So it's not quite clear that it even exists. So here is open true-false question. So maybe these two numbers are just the same. I think it's very likely to be the case, but it's really difficult to prove or disprove. So that's kind of situation here. Okay. So let us do one example just to get some feeling of what is going on here. So let us take for group gamma cyclic group of order 5. Let us do things in characteristic 5. So this is really modular case where representations are not semi-simple anymore. So if I want to discuss representation of such a group, I just need to specify where generator of my group goes. It goes to some matrix. This matrix power 5 should be identity. Where in characteristic 5, so this equation a power 5 equals to identity is equivalent to equation a minus identity power 5 equals to 0. And well, indecomposable solutions to this equation are easy to classify by theory of Jordan normal form. And there are exactly 5 of them. So Jordan cell of size 1, of size 2, 3, 4, and 5, since my matrix power 5 is 0, you cannot have blocks of size 6 and so on. So for example, representation which corresponds to cell of size 3 is determined by this matrix, something like this. J1 corresponds to 1 by 1 Jordan cell, so it's kind of trivial and simple representation. And J5 is exactly one of these projective representations. That's the only projective situation in this setup. And you can try to compute tensor products of various Jordan cells here. Again, if you want to keep your students busy, just give them as an exercise to compute this. It will take quite some time. So, and playing the same game as before, you can try to compute what happens with tensor powers of something. So for me, let us take for something representation which corresponds to the 3 by 3 Jordan cells. Actually, surprise that you get by looking at this tensor product rules is that when you take tensor powers of J3, you are going to see J1, J3, and J5, but you will never see J2 and J4. It's just kind of consequence of my multiplication rules. You see that J2 and J4 do not appear. A little bit unexpected. But now, playing the same game as before, you can deduce some recursive relations for my coefficients. You can solve them. And actually, if you try to solve them, it's really easy to see. So what we have? We have equation for Bn plus 1. It says that Bn plus 1 is An plus Bn. But at the same time, An is the same as Bn minus 1. So equations that you get for Bn plus 1 is exactly very much familiar equation for Fibonacci numbers. So we kind of all like it. So this number is actually exactly what was my sequence Cn prime, which counts number of indecomposable summands. If you want to find dimension of indecomposable summands, you count An with multiplicity 1 because dimension of J1 is 1, and Bn with multiplicity 3 because dimension of J3 is 3. And what you will get is some relatives of Fibonacci numbers, which are called Lucas numbers. It's kind of the same recurrent relation, but different initial conditions. Of course, we all know how Fibonacci numbers grow, and in this case, gamma of V is going to be exactly golden ratio, which is kind of interesting feature of what is going on here. So in a moment, I'm going to define another invariant, which is called delta of V, and for this example, it's just exactly the same thing. In general, it's not, but kind of, I just want you to keep in mind this example for my next definition. Okay, and maybe one more exercise. I mean, try to compute what happens for J2 and J4. So that's it. Any questions? Let's move on. So it's another way, again, to count indecomposable summands. So let us do, the same thing as before. I'm going to assume from now on that my field is algebraically closed. Otherwise, my definition should be modified. So let us define another sequence, Dn of V, and this is total number of summands, but I count only summands such that dimension is not 0 in my base field. So in other words, if my base field is of characteristic P, I don't want dimension of my summand to be divisible by P. If it is divisible by P, I don't like it. If it is not divisible by P, I like it. So it's kind of, maybe sounds like a strange choice, but well, hopefully I will justify that it's interesting choice. So it's really easy to observe that these numbers satisfy inequalities like this. So first one is kind of convective property, and second is just some bound. Feketa's lemma from analysis guarantees that limit existence, limit of this nth root, just as in all previous citations, really exist in this citation. And this is my invariant delta of V I was talking about on previous slides. It's kind of my new invariant I want to talk about. Okay, so let me just say kind of the same thing, but a little bit differently. So let us start with some indecomposable representation of some group, or maybe supergroup. And I'm going to say that a representation is negligible if its dimension, again, 0 in my field. So it's kind of, in this language, my definition says that we are trying to count non-negligible summands and tensor powers. So this is interesting even in characteristic 0. In characteristic 0, if you deal with supergroups, then you should take at this place superdimension. And superdimension very well might be 0. And kind of things of superdimension 0, they're negligible from my point of view. Okay, so, and non-negligible if it is not non-negligible. Reason why this choice is kind of a good choice, I mean, this particular choice of counting non-negligible summands is a good choice, is, at least in big part, it's based on this observation by Dave Benson. I think it's more than 40 years to this observation. So observation is that negligible representations, they form tensor ideal. So very much in the same way as projective representations before. So if you take negligible, so negligible means that all indecomposable summands have dimension 0, tensor with anything else. So all summands in the result are also going to have dimension 0. So that's the property. And this kind of, well, really helps with this definition. So, well, maybe once again, so my sequence Dn of V is total number of non-negligible summands in tensor power n. And I hope to tell you something interesting about this sequence. Or maybe really about nth root of this sequence. So some properties which are really easy to deduce directly from the definition is that this invariant delta is sub-additive, sub-multiplicative. You will get 0 only if your original representation is negligible. If you get something greater than 0, then you get something greater or equal than 1. So this is kind of elementary properties. So here is a theorem which says that things are much better than this. And actually, to state this theorem is, well, easy, but proof requires really some non-elementary techniques. So first of all, this invariant is really additive and multiplicative, kind of good thing. And another thing that possible values of this invariant, they are very much restricted. So possible values are, well, it's linear combination of quantum numbers with non-negative coefficients. So, quantum numbers is something like this, where Q is some very, very specific root of unity. But in practice, it means something very, very concrete. So, for example, in characteristic 2 or 3, possible values of this invariant are just integers. Or if you are in characteristic 5, we've seen that golden ratio is going to appear, but basically that's it. So kind of the only possible values of this invariant are non-negative linear combinations of number 1 and of golden ratio. That's all. So there's no other options here. So maybe something that is going to be useful for me later on is that kind of these values they always form discrete subset of real numbers. It's always just a discrete subset. That makes sense? Okay. Well, let me do few examples just to illustrate what is going on. So we did this example with cyclic group of order 5, characteristic 5. My representation is J3. So in this case, both invariants gamma and delta are golden ratio. My sequence is just sequence of Fibonacci numbers. Maybe another example. Let us take cyclic group of order 8. Characteristic 2 to make things interesting, and let us take for the Jordan cell of size 5, and let us play the same game. And well, this example shows that gamma and delta they are not always the same. So kind of one of them is 3, another is 1. And sequence Dn in this case is yeah. No, there is absolutely no reason for this for them to be the same. It's just kind of in the only examples that we considered, they happen to be the same. So I mean, we considered just one example so far. So if you consider one more example, you immediately see. Yes, yes. So there is an inequality. Well, any projective. So if P divides order of the group, then any projective is going to be negligible, and this gives you some inequality. It's very good question. Yep. And actually, please ask more. Okay, so this is Z-mod 8. Z-mod 9. So again, let us play the same game. So characteristic is 3. Let us again take this representation which corresponds to Jordan cells of size 5. Again, in this case, you can compute gamma and delta, and they're given by, I mean, again, different numbers. You can compute explicitly the sequence Dn of V. And there is something I want you to observe. We've seen this sequence before. The sequence appeared before in the very beginning of this talk. And this is not a coincidence. It's, I mean, it's really, there is a good explanation for this. So it's kind of the same sequence that we've seen when am I supposed to finish? Okay. going to finish. Thank you. My phone wants me to stop. Anyway, I think I'm done. You can use various things out of our theorem. So let me just say one example. So assume that your n characteristic 2 and dimension of your representation is 3, or maybe your n characteristic 3 and dimension of your representation is 2. Here is kind of what our theorem implies. There are just two options. Either all summands of this tensor power, either all of them are non-negligible, or another option, every tensor power contains exactly one non-negligible summand. So basically, challenge, I mean, try to prove it on your own. So that's kind of typical consequence of this theorem. Okay, so let me stop now. Thank you very much for your attention.
Any questions, comments? Yes, please.
So in your last theorem about additivity and multiplicativity of the invariant delta, which kind of ingredient comes into proof?
So first of all, there is some categorical interpretation of this situation. So you can take quotient of your original category by negligible morphisms, not just objects, but morphisms. You get some semi-simple symmetric category in this way. And main ingredient is that we can prove a theorem that symmetric tensor categories with some conditions which hold in this case admit kind of counterpart of fiber functor. So not to category of vector spaces, but to more general category, which we call Berliner category, which is kind of different for every characteristic P. And this invariant delta of V is, well, it has something to do with the image of this under this functor.
So you don't really use the fact that the original category is a category of representation.
So what is important that this category is symmetric tensor category. That's important.
Thank you.
Yeah.
So if you have something which is multiplicative and additive, so you should have something like semi-field, and maybe there should be something similar to tropical mathematics.
Well, it might be related with previous questions. So basically, what is going on here, this delta of V is just kind of numerical shadow of object in some particular tensor category. I mean, I'm not sure that this...
So it should categorify a lot.
Yeah, I mean, basically, the theorem is decategorified version of some categorical theorem.
Great, thank you.
Thank you. I have a question from information theory, but I'll just mention math. So that maybe irreducible representation or indecomposable subspace in this talk of the symmetry group, not just the S3, but maybe generally Sn. And I want to see, could we compute the number of specific irreducible representation of Sn arrays from the decomposition of the tensor product as you mentioned in this talk. Actually, formally, I just want to know the computation of the evaluation of the so-called chronic coefficient. So I want to know
which coefficient?
Chronic
coefficient.
Yeah.
Yes.
So I want to say, is this theory, tensor category theory, has any relationship to do with the evaluation of the chronic coefficient, or you just make some comment or insights? Thank you.
Yes. Probably there is more than one answer to your question, so let me just give you one possible answer. So there is a notion of stable Kronecker coefficient. So kind of basically when partitions which appear in your Kronecker coefficient, you can add to each of these partitions very long first row. And basically when you add this row, after a while they kind of stabilize. So kind of for sufficiently long first rows, they completely stabilize. And this has categorical interpretation in terms of so-called Deline's category representations of symmetric group ST. So where kind of subscript is not an integer anymore. It's just kind of formal parameter or something like this. And actually, so In this category, multiplicities are given by the stable Kronecker coefficients. But actually, there is also a way to go back. You can start with this category and try to get some information about your favorite symmetric group, actual symmetric group. There is a functor from this abstract category to actual representations of, and this gives you some formulas for this coefficient. So this might be useful.
Thank you.
Questions?
So you had these transcendental numbers showing up when you looked at SL2 at characteristic P. Do you know if something similar happens with quantum SL2 with root of unity?
Yes, so quantum SL2 at root of unity is actually, it's going to behave very similar to finite groups. So I mean, to this modular situation in finite groups. So what happens if you take the tensor powers, after a while you are going to see some projective module, and after this kind of projective modules will take over kind of things. So you are not going to see kind of the strange transcendental powers. But it's still, you still have many interesting questions about this decomposition. And actually there is a person you can ask, I mean, who knows a lot about this here. So Kola wrote several papers about this. No, yeah. It depends on your original representation. So you can start with the representation. Yes. Yeah, but you can start not with a reducible representation, but with something complicated. You can start not with tilting, you can start with something.
I very short question. Can you show your slides? Just
Let me see where something interesting is going on. So
just
something interesting, this is really something interesting what I wanted to tell you. So remember we had this kind of strange situation when we computed Bn, and it was dimension of V divided by n to some powers and so on. This Dn sequence behaves in much simpler way. So basically it always squeezed between delta of V power n and delta of V power n. And this is kind of, well, it's much simpler actually than my original sequence. That's really surprising property, I would say, so or interesting property. So I think the slides will be uploaded somewhere. So no.
no,
No.
this will be a quest. Find on the internet these slides. Thank you very much. Thank you.
Thank you.